morning. Good morning, everyone. Welcome to another episode of Xah Talk Show. Today is September 24th, 2019, Tuesday, 9 o'clock a.m., 10 after 9 a.m. San Francisco time. And I just woke up 10 minutes ago. I'm trying to keep a schedule now, so every day is going to be 9 o'clock in the morning for this week. This week, every day, 9 o'clock in the morning is the start time of Xah Talk Show. Let's check if I'm alive. Yes, indeed. And nobody is here yet. And I think I'll be back in 5 minutes. And I just wake up and I have to. I'm not awake yet. My eyes are not open yet. So I'm thinking 5 minutes, okay? 5 minutes. Or, so guys, post something, post questions, or either I come back in 5 minutes or we start right now. You post some questions and we can start right now. Or I come back in 5 minutes. And we have, pick a topic. So, okay, pick a topic. Be right back in 5 minutes. Okay, so 9:15. Okay, 9:15 a.m. San Francisco time. Okay, guys. So pick a topic, and we'll start. Then let me show you this screen. Okay, yeah. So Okay, guys, I'm back. No topic yet. No topics yet. So I'm thinking we're gonna talk about. I'm gonna give you a introduction to how compiler works. So introduction to how compiler works. If you like that, just type it. Okay. Now type a topic. Okay. Type a topic, or we can talk about how compiler works. Otherwise, I'm just going to start random. How compiler works for how compiler works for beginners, or I'm just going to show you random. Good morning, Sergey Lin. It's a great topic. How compiler works. Okay, let's talk about that. Okay, let's just start on that topic impromptu. Where you from, Sergey? I haven't seen you before. So okay, how compiler works. Maxerator. Good morning, Maxerator. Maxerator, you are from Russia, right? Okay, so how compiler works. So let's go to how compiler works. Let's go to language tutorials, and let's move this here, and let's move this here, and from Sergey Sergey Lin. Sergey is also from Russia. Maxerator is from Tacoma, Washington. Where is Tacoma? Washington State, right? So how compiler works? Let's see if I have it somewhere here. Okay, let's see how compiler works. So this is going to be an introduction to how compiler works, parsing and compiling. This is not technical. I'm just going to give you a overview how the whole thing works. Along the way, you'll learn about grammar, programming language grammar, and also some theoretical computer science. Because when you start to talk about compilers, there is a lot theoretical computer science, very interesting stuff. You start to learn about automata, regular expression. That is the origin of regular expression. It's part of parsing. And okay, let me find the article first. Keyboard Talk Show. Should be here. No, okay. So let's find the article first. Programming Language Tutorial Index. Hacker Code. Hacker Code. How compiler works. There it is. Okay, hold on a second. Okay, Maxerator says interpreters in language like TCL is nothing more than functions. There is no fast AST. Okay, so you already know about it, because I do not fully understand it. Now, AST stands for Abstract Syntax Tree. Conceptually, I understand what it is. It's a tree. It's a tree of the structures. But have you ever written a compiler? Or I, I have not, so I don't really understand how it is. But anyway, so let me just begin the introduction how compiler works. So compiler, what is compiler? Compiler is, for example, let's start a Python. Let's say Python code. Okay, so Python. So open a new shell, let's say print, let's say Python 3, okay, Python 3, and start a new shell, new buffer, 1 plus 3, that's Python code, run it, and we got 4. Now, so the compiler's job is to, they have to look at the code. Okay, I haven't been coding Python for a while, so let's say x equals to 3 plus 4, then print x, run it, the result is 7. So when a compiler, first of all, you have to read in the source code. So this is the source code. You have to read it in, you have to parse it, then after you parse it, then you have to turn that into the machine language, into the machine language, so that the CPU can actually run it. Then you execute the machine code, then it outputs 7. Stack languages like Forth. Okay, I can talk about that, but the compiler topic will probably just take over for, take an hour. So anyway, so compiler. So there are 2 steps to first of all, compiler is a program that takes a source code. So let's write it down. So whenever, if we write it down, then we have more organized topics for the show. Compilers. Okay, compiler is in the source code and output another code, typically assembly language, output another code in another language. Okay, it basically translate one language to the other, but typically the output is assembly language. Now assembly language is the lowest language for the machine to read. Okay, we're gonna explain that. So okay, so compiler is reading a source code and output another language code. Typically that language code is assembly language. Assembly language is a language for the machine to read. What does that mean exactly for the machine to read? We're gonna talk about that. So what does assembly language mean? What does it mean to say for the machine to read? Okay, for the machine to read, because human languages include, well, programming languages, high level languages such as Python, it's read by human. You understand what this means. X equals to 3 plus 4, and you understand what print means. Typically it's based on English. But what does machine understand? What does machine read? Okay, you can think of a machine as abacus. Okay, this is the most basic understanding of a machine. Abacus. Have you guys seen an abacus? Let's just search for abacus. ABACUS. Okay, and let's search for Xah abacus. I have a page written about abacus. So let's look at images. What is this? Why why are these pages, those photos are me, but I don't have this page on my website. So why are they showing all these abacus picture? I don't know. But if you go to my okay, so wait, so search images here, and we don't want images here. So abacus Xah, so this page. So here is an abacus. Abacus, they are basically just stones on a string. You can manipulate. You can push the beads up or down. Okay, that's how you tally, how you count. It's almost like it's like a counting machine. So you push a bead up, then that means one to you. So typically, how this works is that you start here. So this if you push this red bead up, then that means one. If you push two beads up, that means two. So you got one, two, three, four. Then for five, you push the top row down. So that's five. So if you have this pushed down and the bottom one pushed up, that means six. So in this column, you have a total, the maximum is 9. So if you want 10, you push the bit to the left of it up. So that's abacus. So this is a machine. So abacus is one of the most easy to understand machine. Now, algorithm is all about machines. You see, what algorithm means, now this is important. This is a definition of algorithm. What algorithm means is that algorithm is a recipe. It's a typically written down recipe that tells that is a step-by-step instruction to some machine. Okay, there's always a machine involved. When you talk about algorithm, implicitly it means a machine. Okay, this is important. What is algorithm? Okay, algorithm is a step-by-step instruction that is a written step-by-step instruction that instruct a machine to do something. Okay, now when you talk about algorithm, important, this is a thing we usually forgot when we talk about a algorithm. It always, ALWAYS, involves a machine. Okay, so for example, in our daily life, when we program Python, JavaScript, C, or whatever Java language, there's always a machine involved. You see, and this machine is typically modern computer machine, the CPU, whatever chip it is. Apple on Intel chips, on different chips, they are actually different machines. So compiler read in the language source code and churn out this typically assembly language for that particular CPU. So you can also, for example, you can write a compiler so that compiler reads the Python code and output instructions for this abacus, like assembly language for the abacus. So depending on what machine, the assembly language will be different. So what is assembly language? Assembly language is basically instructions to control the machine. For example, we have a abacus here, and what are the instructions? The instructions are, for example, move to the column 1, push the beads up or down. That's instruction. Or move to the left column of the current column, push beads up or down. That's instruction. So you can imagine we have this abacus, then we have what's called instruction set. Instruction set, a set of instructions. The instructions includes moving, let's say moving a robotic arm, to a column and push beads. That's the instructions, and that makes up the assembly language. So assembly language is kind of the low level language that controls the machine. Okay, assembly language is a low level language that 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 execute instructions of the machine. Abacus is a example of a machine. Now there are many other machines. For example, CPU is a machine, and modern computers such as CPU or your calculators or the chips in your microwave, those are all machines, and those machines are very, very, very complex. It's hard to understand, but in principle they are just like an abacus. You have a instruction set. Every machine has a instruction set. Okay. So back to the compiler. Compiler is a program that takes a source code in a particular language and output to a machine language. Okay. And now, now, usually there's some distinctions about compilers and interpreter. Computer scientists call them interpreter. So what's the difference? Compiler. So remember, compiler takes the input source code, output to another language. So from higher, basically, usually from higher level language to another language. Now in JavaScript, for example, we have many so-called transpilers, but they are just compilers. Okay, transpiler, they are basically just compilers in principle, by principle. For example, JavaScript, for example, TypeScript takes in a source code of TypeScript source code and output JavaScript code. That's TypeScript compiler. Then your browser takes the JavaScript code, compile it, and output the machine code. The browser. That's the browser's job. You have a JavaScript compiler in browser. So compiler takes a language source code and output another language code, typically low level. And another thing is about there's a word interpreter. So with the difference typically between compilers and interpreter is that compilers reads the entire source code and output another language code. Now interpreter typically they just take one line or few lines of code. For example, when I run this Python interpreter takes this source code and output a machine code and run it like right away. Run it. Typically, compiler do not run it. That's not compiler's job. But when you talk about interpreter, that's uh, part of the process. So that's a minor difference between compilers and interpreter. For example, but the differences are basically become less and less today. For example, in Golang, so here is the Python code. Let's copy it. So Python code. Let's go back here, and let's make another Golang code. So Golang. So let's go to Golang, and let's print. Let's say variable x3 plus 4. Okay, and print x. Okay. Run it. 7, you see. So in Golang, this is Golang compiler, but actually it also functions as an interpreter. So instead of output another source code, it actually it output another language code, but it runs it directly. So the Golang compiler is both a interpreter and compiler. So that's a kind of the semantic differences between compiler and interpreter. Okay, so let's summarize. Am I doing good? I think I'm. Let's see. Okay, 27 minutes. We are kind of too slow. Let's see the comment. Good morning, Kathy. There does not have to be a machine to have an algorithm. Euclid, no, there needs to be a machine. So this is where importance of Xah Talk Show comes in. Now remember, compiler always involves a machine, always. Uh, well, I mean, you might say there does not need to be a machine. For example, Euclid algorithm (LCD). LCD is least common denominator algorithm, qualifies as software algorithm. Yes, but compiler always algorithm always involves a machine because what is the algorithm for example 1 plus 3? What is a machine? Where is a machine? When you do 1 plus 3, or suppose you want to sort a bunch of numbers, so 1 to 5. Okay, you have 5 numbers, 1, 2, 3, 4, 5, and they are randomized. You want to sort them. Where is the machine? The machine is a virtual math machine. The machine is math. You know, that is a machine, because without machine you don't have algorithms. Because remember, if you look up a definition of algorithm, the definition is basically going to be step by step instruction to do something. You cannot do something if you do not have something to do with. If you are cooking, you have a recipe, you need ingredients, you need the cookware, you need the stove, you need a fire. That's the machine. So this is kind of importance. Yeah. So when you talk about math, math things. For example, sine 3, sine cosine, trigonometry, or any function, x squared. Okay, x squared. If x is 2, then the result is 4. Where is a machine? Okay, in math you don't think of a machine because it's just a function. But when you actually want to tell the computer or someone to actually do it, how do you get 2 to 4? You start to need a machine. You need a machine. It's not, you need a machine, and in this case the machine is kind of a virtual math thing. So anyway, compilers, interpreters, algorithms, and the recipe. Now let's talk about recipe. Let's talk about languages for a moment. So remember, compilers reading a language and output another language. Now what are languages? Languages is a writing system that of instructions, basically instructions. Just like human languages. In English, French, Chinese, Japanese, you have different languages. Same thing for programming languages. So Python, Ruby, Perl, Java, they are basically instructions. Okay, they have precise meaning. And the instructions, the low-level instructions, machine is the kind of like abacus. We talked about instructions where like move this column, these bits up by 1, or move over here and move another bits up or down. Those are instructions. So, and also another thing about CPU is that you might have heard of instruction set in a CPU, like Intel i5 chip or something. Each CPU today, they have a instruction set. Instruction set is a collection of basically instructions or commands that tells the CPU what to do. So put the whole thing together. When you run a Python code on my Mac, on this particular model of Mac, it has a CPU inside, Intel 5 or whatever. It has an instruction set. So the compiler reads the Python code, output a machine language. This machine language is feed to the CPU. This machine language, is basically instruction sets. Tell the CPU what to do. Then the CPU runs it. So that's about compilers. That's the overview of a compiler. So okay, so I think I'm getting too slow, bogged down. So let's read about it. So compilers and interpreter. Interpreter is just like a compiler, except that they also run a code. Okay, so you have assembly language. Assembly language is a low-level language that still makes sense to human. Okay, so here is an example of assembly language. Now, assembly language typically have three items. Like each line is just three items. For example, this move AL661H means load AL with 97 decimal. Okay, so that's an example of assembly language. So source code of assembly language is just like that. You know, basically three one instruction per line. Now, what are those instructions? Basically, they are like you know, put this number in this place or read a number from that place. Things like that. That's assembly language. And what is a machine language? Machine language is lower level than assembly. Machine language is a set of instructions executed directly by CPU. What it looks like, a machine language just looks like a bunch of zero and ones. It's all just 0 1 0 1 0 0 1 1 1, you know, like that. Okay, so let's skip that. So compiler. Okay, let's talk about the structure of compiler. So I thought about learning assembly, but I don't know what can I do with it. It can do anything a programming, any software does. You see, any software you run through a compiler that becomes a machine code. You know, so it basically is just lower level. It does anything software does. Every software, basically every software had, you know, eventually on modern computers they become machine code. Whenever you run, you know, any language, assembly or whatever, they become, by compilers, they eventually become machine code. You know, a bunch of zero and ones. Why 0 1? Why a bunch of zero ones? Because that's what the CPU reads. You know, because CPU, we are using electronic computers. You also have non-electronic computers, like such as like quantum computers and DNA computers. You know, biological computers. They don't use electronics. You know, they are not electricity. But for our computers, they are electronics, and typically they are zero and ones because electricity is either on or off. That's how it works. So that is why machine code is just zero, a bunch of zero and ones. So, but remember, machine code, assembly language, or higher level language like Python and Java, they are kind of the same. I mean, they are just the same. They are just in different languages like Chinese, English, you know, Russian. Python, Ruby, Java, JavaScript, C, they are high level languages we understand. But the machine language, assembly and machine code are machine languages. So they are, you know, they are kind of the same. The only difference is that machine languages are unreadable to us, to humans, because they are too low level. Um, and we have showed an example of assembly. You know, it's just things like that, like read this number from this registry and read that number from that registry and add them together. So that's assembly language. So you can see some examples uh, of other assembly languages. So here is Wikipedia. You can see some examples of assembly language. Let's see. So here is a example of what is this assembly language. Uh, Yeah, here's some example of assembly language. Let's look at this. What is this? Each line is basically one single instruction. The things on the right side are comments. These are the comments. Anyway, I don't know. I don't know assembly language. So actually, we are going too slow because there are a lot of things. So okay, so we know what is a compiler. We know what's an interpreter. We know what's an assembly language. We know what's a machine code. So far, all the things that's important because that's we talk about algorithms, what it means exactly, and we so let me repeat. Algorithm is a step-by-step instruction written down in some language. That's what algorithm is. So algorithm. So you can have So algorithm always implies a machine, and in turn, it always implies with a particular language, one or more languages, because algorithm is a step-by-step instruction and it's not verbal. It has to be written down. Typically, we assume it's written down. So, we have a recipe, and when it's written down, it must be in some language. So it gotta, be a language, and the language is basically instruction set. So that means it has to work with the machine. It has a machine somewhere. So that's what algorithm. Now, let's talk about compilers. Now, when you compile like today's Golang JavaScript stuff, they have two steps in basically. They have analysis and synthesis. Analysis step is basically you read the source code, you understand what the source code means exactly, and you generate a tree. Let's see if I have that Golang. So anyway, so here is the source code. For example, this is Emac Lisp. Emac Lisp compilers, they have to read this source code and generate. Then you read this source code, then typically you output in what's called AST. That stands for Abstract Syntax Tree. Not just that, more information than that. But basically, you read the source code, you output in a format, in a more logical format. Okay. Then the second step of compiler is synthesis or code generation. So the second step reads the output of the AST. Then it tries to convert it into the target language. Maybe it's assembly language, maybe it's a machine language, or maybe it's another language. For example, many compilers today, they compile, for example, Golang to JavaScript, or JavaScript to C, Lisp to C, like there you are converting languages. So two steps. One step is basically just reading the source code, read it, understand it, output in a format that's easier to understand. Then the second step is to read that format and output to whatever target language, machine language or whatever. So here is the two steps in more detail. So the first part here, so source string, you start with a source code string. Then this part, the first part of compiler's job is called parsing. So you parse it. Parsing has three steps: lexical analysis, tokens, syntactic analysis. Okay. Anyway, that's parsing. Then you generate a parse tree. Yeah. You output a parse tree. Then the second step, generating code. That task is typically called compiling. So you take the parse tree and you output to your target language. Okay, so hold on a second. it's kind of too slow, and I just woke up and we got 9 people watching. So actually we are too slow. So I want to jump to some interesting parts. That is the grammar, formal grammar, and formal grammar, Backus no form, and um, and context-free grammar, because these are high-level stuff. I'm much interested in those things, and these are also interesting stuff. So let's talk about that. So so let me try to cover them. So compilers, remember there are two stages of compiling. The first part is usually called parsing. That is, you read the source code, you output to a format that you understand it. You read the source code, you reading the source code is not easy. For example, here's a Emac Lisp code. So how do you begin to read it? That's the job of the parser. So let's for example, let's say this line. So this line said something, then something something. You actually you have to write a program that reads each character. You read this character, then next character, and so on. This is every compiler, every parser does this. You have to read character by character. Then you have to. So how do you do it? I mean, like if we are doing this from scratch, how do you do it? You have to, you that's a parser's job. You read each character by character. Then you use grammar to understand it. We will talk about that. Then you finally output a format. When So compiler has two stages: parsing and code generation. Okay, parsing is when you read the source code and outputting a format you understand. Then the code generation takes that format and output to another language. Uh, okay, so the interesting thing is, how do you parse? Like how do you parse? Uh, so let's uh, so let's see what we have here. Lexical analysis, non-deterministic finite automata, and deterministic finite automata. Okay, stuff. Syntax error handling. Okay, so there's a lot to it. So let's talk about parsing. Parsing. So I'm just I'm just giving you a overview how this works in theory, kind of a theoretical overview. I don't know the stuff in detail, so that's one of the things I'm trying to learn. Let's see what we have here. Comments. Mixerator says the concept of assembly syntax is easy. It's all the machine level details that are difficult. Sergi says there are nice games by Zachtronics, TIS-100, Sengen IO, Xah Punks. If you want to get the feel of assembly programming in a fun way. Good morning, Bartholomew. Who is shaving their head in the background? Oh, it's they are lonely in the moon. People are lonely in the moon. Parse is breaking up the stream of syntax into keywords by use of case statement. Yes. Parsing, before. So, for example, this is a Emac Lisp language. You have to parse it. So, parsing essentially means understanding the code. But where do we begin? Like we don't. I mean, how do you start to? So this is a hard task. So let's go back to for example, Golang. Okay, so showing browser. So we have Python code here. We have Golang code here. You Suppose you have this task to do. You need to write a program to parse it. Where do you begin? You have to read each character, but then what? So so this is a tremendously difficult task. This is actually a very difficult task. And so to do parsing, actually, this involves, first of all, this parsing involves understanding a language, because each language is different. So that means a language that comes the concept of grammar. Each language needs to have a grammar. Compiler phrase. Okay, so let's see. Parsing phrase. Okay, so parsing phrase, they have parsing can be broken down into three steps: lexical analysis, syntactic analysis, semantic analysis. um, okay, I'm not so lexical analysis is the first step of parsing. It takes a input string and lexical grammar, and then breaks the input string into a sequence of syntactical units. Each is called a lexeme or token. Um, okay, so yes, Max Rater said it. Max Rater is great. So Max Rater is telling us parsing is breaking up the string by syntax into keywords by use of a case statement, and parsing has to go character by character to break up the syntax into tokens. It uses BNF as a rule set to do this exactly. Um, I'm kind of stuck. I don't know where am I going with this. Actually, I should know this. I should know this better, so that will be more fluid. But the problem is not that's not problem, I mean, sometimes even something I know, I got stuck. I got stuck because I don't know. I lost track of what's interesting things I want to say about it. Parsing. So anyway, so parsing. You have to, when you parse a language, you have so many different languages, and the difference between Python, Golang, Ruby. That's all the differences in languages. So first of all, you need to have a grammar for a language, because, for example, in Python, you can easily have syntax error. For example, you cannot say, for example, if you put the two things in the same line, that will not work. That will not work. But how do you know it will not work? As a human, well, you need a line here, but you have to tell the machine. That's a thing, because compilers don't ask you, oh, you have to. So that's part of the parsing, part of the compiling. Parsing the code, then you generate a new code. So that's part of the algorithm jobs. So the parser have to know about all the rules. So here comes the concept of grammar. So for every language, you need to have a grammar. A grammar means basically rules that machine can understand, that specifies which syntax is correct, which syntax is not correct. Okay, so parsing is actually fairly very complicated. In fact, that's the foundation. That's kind of the foundation of computer science, and it is also the most critical part, practical computer science, especially in the early days. Like today, we don't think about compilers or parsing at all. Like if you are a web dev, you almost never in your life in today's programming you have to work with compilers. You have to, like, you don't even have to understand what exactly compilers do. You can be a software engineer, for 10 years, 20 years without understanding even basics of compilers, because you don't need to, because it's already written. You have Python compilers, you have Ruby compilers, you have every compilers. But you have to begin somewhere. Somebody has to write a compiler, it's, and compiling tools. So today, if you want to create a new language, then you need to write a compiler. So compiler, like we mentioned before, there are many. It's very complex. You have to read the source code. You have to understand grammar. Grammar is very complex. Actually, there is an entire. You can learn. You can spend a few years about parsing itself, about grammar, and grammar is a topic that's very theoretical computer science. I mean, you can study grammar in your entire life. Because it connects to theoretical computer science and computability and things like that. And yeah, so the whole topic is very interesting. For example, we talked about machine language. So Turing machine, for example, that's a machine language. And lambda calculus, for example, that is a programming language. And they have to do with theoretical computing, but they are also related to what we are talking about here, like lots of it. So we so what I was talking. So parsing. What was I talking? So parsing. So let's talk about parsing. Okay. So good morning, Boyer. Okay. So you have to so you have to so every language, programming language. So yeah, we were talking about relations to theoretical computer science, about Turing machine as a specific machine, and lambda calculus can be considered as a specific programming language that is written down form of instructions. And so let's talk about grammar. Okay, so in order to parse, so we were talking about how compilers relate to theoretical computer science, and how today most programmers, you don't have to know anything about compilers at all to work in software, for 10 or 20 years. But some people have to do that. Yeah, so back to, if you are creating your own language, like today there are so many new languages. There's a nim there's a crystal, that basically, that's like there are so many new languages, Haskell, and others. So in order to have a programming language, if you are going to create your own programming language, or Lisp, you have to have a grammar. A grammar. So what is a grammar? Okay, yeah. So you have to have a grammar, because without, how do you begin to parse? There's you cannot verbally explain to the computer, what is your code. So you have to have a grammar. Grammar is a specification of the language's syntax. Now, how is that done? That's so complex. For example, how can you possibly tell? Imagine we have a Python code right here, right? We have a Python code. It looks us it to us, it looks very simple. X equals to 3 plus 4. How it's so simple. You cannot be simpler. Then you say print parentheses something. But the thing is, you have to explain this to a machine. So that is a grammar. So how do you understand how is grammar? So let me explain how grammar is, and how it works. Yeah. So okay, so let's explain how grammar is. Every programming language needs a grammar, and so grammar we have. So let's talk about this Backus no form. Okay, Backus no form. So formal grammar is almost always written in a notation called Backus no form, or a variant of, shortened as BNF. Okay, Backus no form is a notation used to specify the grammar of a computer languages. Okay, for example, let's say we have a language for addition. For example, 3 plus 4 or 6 plus 2 are both valid source code. Yeah, so let's begin simple. Now let's forget about x equals to something. Let's forget about print something. Let's just focus. Let's say you are creating a new language, and let's say the entirety of the whole language, the syntax is every line must be this form. Okay, a plus b. Okay, every line is in that form. So, and what is A and B? A and B must be characters like 1 to 9, 0 to 9. Okay, that's suppose that is your language. Now, if you add a space here, then it's incorrect. It's a invalid syntax, for example. So, suppose this is your language. Very easy to understand. So for that language, then you specify the grammar for that language looks like this. Okay, it looks like this. So you have S arrow sign number. That's one line by itself. Then each number can be one of 0 to 9. Okay, so this is actually the full specification for your language. You know. So what Okay, so actually, we need to go to detail about this. Actually, I'm not good. This. I'm not good. I'm not good doing this topic. Yeah, I need to be much more familiar to do this better. Yeah. I think I kind of failed here. I think that's we already talked about for 1 hour. Um, I wanted to go to so many interesting things here, but it's I'm not ready to do it. I don't think so, because yeah, I'm not. I don't know this subject too well, and this is my first time trying to explain it. And it should be able. I should be able to at some point. You know, like for example, I can explain JavaScript well and or Emac Lisp because I know it so well, but not so much with this because this topic. There are so many interesting things I want to talk about. But right now, because I haven't done this, and also because I don't know this too well, so that I cannot just like have so many things in my mind I want to tell you. Like every time after a few sentences, I have to read it, then so it's no good. So I think that's I'm not doing good today for this subject. Uh, Okay, so that's I think that's a good point. I'm trying to I try to yeah I'm trying I made it I'm trying to uh like it's almost like I'm trying to explain to 10 years old kids. So I should go faster, much faster. Then it'll be much better. So okay, let me try that. Okay, so anyway, so this is one example of Backus no form. Okay, so at least you know that. Okay, this is an actual example. Like if you actually look at programming language grammar, for example, if you go to let's go some practical things. Let me just talk about what I know. Okay, Python documentation. For example, we see a practical example of grammar specification. Okay, so if you go to Python, and actually this is practical because when a lot of you are Python programmers, and you have to read documentation every day, and often you will see these. Okay, stupid Python, you need Java. Wait, let's just go to the doc. Come on, go to the doc. What's going on with this? Click. Stupid Python. Okay, here's the Python documentation. Okay, if you are a Python programmer, you are probably you've seen this 1,000 times. So now you go to language reference. Language reference. Okay, that's what Python calls it. But if you go to language reference, then you will now. Okay, so this is why this is important. Okay, we were talking about compilers and Backus no form. So aside from, even if you do not write compilers in your whole life, all this information are very useful, because once you understand, the outline of how compiler works, what does it involves, the Backus no form, the parsing, the code generation, the grammar specification, then in real life you understand many of the terms used in, for example, Python documentation. For example, you see lexical analysis. Now, lexical analysis just means like parsing. Like you read the source code, you are trying to understand what they mean by the grammar. You see, so in Python doc, so you see lexical analysis. You see, hold on a second. So it says Python program is read by a parser. Input to the parser is a stream of tokens. Token just means, what is a token? Okay, token means, for example, let's say, let's go back to Python. Let's go to token. Token is basically just means a word. Okay, for example, this X is a token. X is a token. Equal sign is a token. 3 and 4, they are tokens. Plus sign is a token. The full word print is a token. The left parenthesis is a token. X is token again, and right parenthesis is token. Now that's Python. Now in Golang, package is a token, the whole word. Main is a token. The double quote for string is a token. Okay, that's a token. So curly bracket is a token. So you see, that's what token means. So token means a token is kind of the smallest unit of a thing in a programming language source code. So that's what token means. So the first stage of parsing, you read the source code character by character, and then you want to break them into a sequence of tokens. So for example, if I'm trying to write a parser for Golang, then the first step, I will have package. I'll have a sequence of tokens that will be package, main, import. Then this whole thing will be a string as a token, or sometimes 3 tokens, like the double quote, then FMT. I think the whole thing is a token. But anyway, then function main, then parenthesis, that's a token. That's the first step of parsing. You break down the source code, a sequence of characters, into sequence of tokens, and this is called tokenization. This is part of the compiler process. Token. So anyway, so go back to read the Python documentation. So you have line structure, logical lines, physical lines, comments, enclosing declarations, and stuff. Okay, so that's a practical thing about parsing. And okay, it looks like I'm lost again. So tokenization. Then okay, let's see grammar. Okay, so let me go to let's go back to Python documentation and white space between tokens, other tokens, identifiers, and keywords. Let's see. So there it is. Okay, here is an example of grammar. This is this is the Backus no form we are talking about. So a grammar, you have actually, we need to explain what Backus no form is exactly. We haven't done that yet. It's it's extremely interesting. But anyway, I think we're gonna stop on this because I am not doing good here. It's extremely interesting uh, because there's so much I want to talk about that because I want to talk about the origin of regular expression. I want to talk about the hierarchy of grammars, and what it means for what does it mean to be a context-free language. Um, anyway, so let's do this sometimes again in the future when I know better. Okay, so Dingo, thank you, Dingo, and thank you, Maxerator. BNF is a pattern matching, so it often uses case statement to match rules. Exactly. So BNF. So Maxerator, you have experience. Have you ever written a parser or compiler? Looks like the stuff. So Maxerator says BNF is like pattern matching, so it often uses case statements to match rules. Exactly, it being the parsing is extremely interesting. I mean, wait, hold on about parsing. So parsing, let me talk about this. Parsing is reading a source code and output reading a source code and outputting a format you understand. Once you analyze the source code, like tokens, what are the tokens? After you got the tokens, sequence of tokens, then you follow the grammar, then you generate a tree. Okay, basically, that's parsing. But before you talk about parsing, there's things about grammar. Now that's about theoretical computer science. This is about formal language because you see here we see an example of a grammar. So what does it mean? What does it mean? So a grammar is basically okay. It's basically many lines, and each line is a basically a you can think of it as a find replace rule. So think of this as replace. Whenever you see the word number, you can replace it to 0. Okay, that's example. Or this is one rule. Okay, so a grammar is a set of rules. Okay, each rule is kind of like a find replacement, like string find replacement. You find a word and you can read it. This rule says every time you see number word, you can replace it by 0, and so on. So that's grammar. For example, in Python here we see the same thing. So it says every time you see the word string literal, you can replace it by by okay, here the grammar becomes more complex, but basically it means you can replace it by either a short string or a long string, and possibly with a string prefix. Okay, that's one rule. So what does short string means? We can find it. So short string, you see here this line. So short string, every time you see short string, you can replace it by by either a single quote, then followed by short string item, one or zero or more of it, then followed by another single quote. Okay, let's magnify. Okay, uh, so here's a rule. So that's one of the rule, or or these. So that's an example of grammar. So each line is a rule, and each line is a rule. It's basically a replacement rule. On the left hand side, whenever you see something like that, you can replace. It's your choice. You can choose which rule to apply. So you begin with a in formal grammar, you begin with okay. In formal grammar, in the Backus no form, in formal grammar. So again, let me summarize. A grammar is a bunch of rules. Each rule are typically just one line. So and each rule is basically find and replacement. Now there is one rule that's special. You call it the starting rule. So you have the starting rule. This rule must be applied first, always the first rule. So this is how you generate the language. So grammar is the grammar of a language. It also generates a language. So basically, this grammar means you begin with something with s. Whenever you see s, you can replace it by number plus number. Okay. So but this is a beginning. So given a grammar, you can generate languages like all possible source code of the language. So so in this grammar, you start with s, just a character s. Then you replace it by number and number. Then every time you see number, you can replace it by a digit. So that's our language there. So in a similar way, the Python grammar there. So what is Python's first rule? There is a first rule. Let's see. String literal. Anyway, so that's about part of it. That's about grammar. So Dingo says, pick up the basic without keys. So pretty crazy how fast you can pick up the basics of software keys despite the key choices being purely ergonomic. That's a method to the madness. So you are using it now? Boyer says, Weebu. I think that's it for today. So so that's it for today. This is botched topic. Maybe we can talk about it next time. Abacus. Oh yeah, these are interesting abacuses. I like to think of when I think about theoretical computer science. I don't like Turing machines. It's silly. I like to think in terms of abacus. Like whenever you encounter some strange ideas in programming languages, or something, or compiling or something, I like to think. I like to understand by to be able. If I am able to break the whole things down, all the way down to abacus. Like imagine if I have an abacus, how does the whole thing works? Explain the whole thing in terms of the abacus, in terms, like down to the lowest level of moving bits on the abacus. Then I understand the concept. So for example, you can understand currying recursion. You might try currying recursion or sorting. What does a sort mean? Or ASCII code. What is ASCII code or Unicode code point? Try to explain all of them down to abacus, because this is logical. This is a logical, because like when we talk about, like, many things today are so abstract. Like when you work with Python, you never think of a machine. When you program in Python, you never think of CPU or anything. But actually, that's what's going on. So if you can, so if you try to think of abacus, um, try to think of everything in terms of abacus, then you understand it well. Like, um, so I think that's it for today. So let me just read the comments and how can I remap? How can I remap Control A to be home across all programs like in Mac? Same with Control F, Control E. Uh, you can do that, but that's you okay. Basiotiad. Bostia says, how can I remap Control A to be home? You mean the home key or the home command? You, I don't think that's what you want to do. I mean, that's okay. There are several questions. There are several questions. I'm kind of still 11 watching. Fourth. Okay, let me tell you about fourth. Okay, wait. Actually, let me finish the. Let me finish about the question. Uh, the sirens are running. So Bastiat says, how can I remap Control A to be home across all programs like in Mac? Same with Control F, Control E. Uh, so are you saying there's a siren running? There's some car security alarms. It's very annoying in modern society. So basically, Bastiat, I think you are what you want is that you want Emacs key binding all across every program on the Mac. I think that's what you want. You already have that, by the way. On the Mac, for example, something. Something in the water. Okay, now let me press Control A. You see, it moves the cursor all the way to the beginning. I press Control F. You see, it moves character forward. Control B moves it backward. So on the Mac, by default, in many text applications, you already have that feature. For example, let's go to the URL field. Let's press Control A. There you go. Control F. You see. Control B. So you already have that on the Mac. I don't recommend using those keys, by the way. Those keys whack your fingers. They give you, you're gonna see a doctor if you do that often. So Boyer says there's no need for you to learn stuff like keys if you are already a master of evil mod. Yeah, but if you really, really, really want to be more efficient, then you might try stuff like keys. So Maxerator, okay, so you read books about compiler, okay, so the rule in BAF are recursive. For example, number is itself a rule that contains number rule. Yeah. So is the Dragon book a good start to learn compilers? Yeah, I read, so in my articles how compilers work. Okay, so I have lots of notes, but all these notes are just for myself. They are not polished in any way. I mean, there's a whole lot in it. When you study parsers, like I said, I'm more interested in theoretical computing, theoretical computer science, especially formal languages. So when you start to talk about grammars, B and F, there's a lot, huge amount of theoretical computer science going on. And parsers, for example, parsers, formal grammar. Okay, formal grammar, you have classification of languages according to their complexity of the grammar, and you have lots of technical jargons for grammar. You have linear grammar, regular grammar, context-free grammar. Yeah, those are the things I like to talk about. Then you have analytic grammar, you have lexical grammar, you have recursive grammar, you have ambiguous grammar. Ambiguous grammar is very interesting because when you study this, then there's a lot of interesting theoretical computer science. It's like, in a word, in a sense, it's a puzzle. You try to solve this puzzle, yes or no. Like you have to answer yes or no. Only one answer is correct. Things like that. And here is another example of a grammar, and this, yeah. So the grammar and parsing is very interesting. So then you have parsing expression grammar. Now the parsing expression grammar is pretty new. It's only invented in the past early 70s. I think I was thinking it's 90s. Parsing expression grammar. So formal grammar and parsers, or parsers is, parsers are techniques to parsing programming language, like we talked about before. When you have a source code, when you have a programming language, you have a grammar. Okay, then you need to write a compiler for it, meaning that you have to parse the source code. So in order to do that, that means you have to write a program. But then there's a lot of problems. How do you do it? That's an algorithm. That's called, those programs are called parser. So there are so many techniques about parsing. So these are algorithms for parsing, and there are many different types of parsing techniques. So there's an entire book written about parsing, about all these techniques of parsing. Which one is better? Which one, their characteristics. So let me show you some of the actually books about interesting books. So Dragon book is the most famous. Yeah, I recommended. I would actually, so the latest version is this one, but I like this cover much better. This is the classic in 1990s. I read like three quarters of it. So here's a table of contents of that book. Yeah, so you can read this book. You can actually buy early version, like buy this version. Okay, it's from 1986. How much? Okay, buy used $14. Okay. uh yeah, now these days the books become so expensive. The latest edition is $130, but you can buy a used one for $14. And there are other books. Today there are other compiler books, so you can read that book. This book is more practical oriented. So if you really actually want to write a compiler, you can read this book. But today there are a lot of tutorials out there. You can actually, if you really want to write a compiler, you don't necessarily need to read a book. There are a lot of information, tutorials and so on. And parsing. So this book is the most. This is the classic, most famous, and most popular book on parsing. Now this book is basically like the Bible of parsing. So it talks about everything that is known to humanity about parsing. Okay, so this book is written by this guy, Dick Grun. Actually, I emailed him a couple of times. He And okay, so and there's a version online free. There's a early edition free in PDF, so you can download and read it. So I recommend it. You go to like, do I have the PDF here? I think I do have the PDF here. So yeah, book website. So you go here. That's his website. So yeah, so just remember the name, Dick Guan. Okay, that's his name. Parsing. Search for Parsing. You'll find his name. So this book I highly recommend it. It's long though. I mean, this is the whole book. The entire book is about parsing, so it's very, very, very technical and kind of boring. So, but if that's the topic you want to know, this is the book. Almost, yeah. This is the book. Okay, so yeah. Good morning, Pablo. So I think that's it for today. So. Uh, Okay, next time. Yeah, I should be. I don't know when. This is a topic I want to finish. I want to be able to write a compiler. I want to write my own language. Create my own language. Even a toy one. Sometimes, in the future, in the near future. So this is one thing that that is my to do. And I haven't done it for like 2 years now. So I need to get on this. So maybe next time, when I'm doing, when I know this stuff, then we talk about that next time. So thank you guys for coming. That's it for today. So I'm going to start to do a video every day, 9 o'clock in the morning. So 9 o'clock, just like today, every day for this week. So that is my schedule. That is, a lot of people want to ask me a schedule. So that is my schedule. 9 o'clock California time every day for this week. Okay. Any more comments, questions posted? And I think I answered all the questions. So that's it for today. Thank you guys for coming. Good morning, Weeaboo. Uh, okay. Thanks. Bye.